All right, so the first chapter is on units and measurements. It's basically an introduction to the course. Physics is a fundamental science, and the goal of science is to explain everything in nature. Okay. We want to explain everything. Okay. So physics wants to explain everything from atoms to galaxies, how they behave. Okay. And I mean, you've been around and you see nature is fairly complex. But it's amazing that even though nature is so complex, there are very few laws of physics. Okay. In fact, there's only 4 fundamental forces in nature, in physics. Okay? The strong force, the weak force, the electromagnetic force, and gravity. Okay? So in principle, you could explain everything based on those 4 forces. Okay? Of course, you don't want to try and explain the motion of your car using those fundamental forces. So you have come up with more approximate laws to explain various things. Okay? So for instance, the behavior of the gas in this room, you don't want to try and use electromagnetic forces to explain those, so you come up with the laws of thermodynamics and all that kind of stuff. Okay? All right, so anyway, so we want to explain everything that happens in nature. And so the laws of physics are surprisingly few, implying a simplicity to nature's apparent complexity. Okay, so here's a slide that shows you various scales that we study. Okay, so here's those bright dots represent atoms. Okay, the size of an atom is roughly 10 to the minus 10 meters. Okay. Here are microscopic living things. These are phytoplanktons. Okay. And their size is about 10 to the minus 6 meters. That's 10,000 times bigger than an atom. So these guys, you can put 10,000 atoms next to each other, and that's how big those are. Here are galaxies, and the size of these guys are 10 to the 16 meters. That's 10 to the 26 times bigger than that. So this object is 10 to the 26 times bigger than that. That's 100 trillion times bigger than that. Okay. And we want to explain all of their behaviors. Okay. So that's what physics is about. And of course, I mean, people that study this you specialize nowadays. You can't cover all bases. Okay. So, but as a whole, we want to explain everything. Okay. This is an interesting image. Okay. This is a scanning tunneling microscope image. Okay. Do you guys know what a scanning tunneling microscope is? Have you heard of scanning? Yeah. All right, so here's what this is. Okay, so, and this is a layer of a sheet of metal. Okay, and you want to know where all the atoms are. Okay. And wherever there are atoms, there are slight bumps. Okay, so here's how we're going to take an image of this sheet. Okay, so I'm going to draw a cross section of it. So here's a side view of the sheet. So here's an atom. Okay. Now I'm going to have a probe. This is just an electrode, okay, a metal electrode. And I'm going to connect let's say 25,000 volts or something like that. Yep. So here's the scanning part. So I have an electrode, and I'm going to walk this across and maintain this distance. Okay. I'm going to walk this across the thing that I'm scanning. When you hit a bump, electrons will tunnel through this gap. So that's where that's scanning. Okay, so you're scanning this across the surface. Whenever the gap is small, you have more electrons tunneling through the gap, so the current is high. When the electrode is over here, the gap is bigger and the current is smaller. Okay. So what is this guy?
It's a composite image of current.
So this, wherever you have a high current, and that spot you mark a brighter spot. So that's, the atoms are proxy for currents. Okay, so that's how you form the image. Okay. All right, anyway, so there's interesting technologies in all the stuff that we do. Okay. And so essentially what I want you to do is, in this class, I want you to question everything. I want you to learn to think. When I say learn to think, I just want you to question everything and try and understand as much as possible, okay? All right. Now, of course, in any science, we make a lot of measurements. Okay? And so we have a fundamental set of units in which we use. Okay? So in science, we have the standard set of units, this SI units, standing for System International. And in 1971, we came up with we decided on these 7 fundamental units, okay, measuring these quantities. Okay. And every quantity in science, everything you measure in science can be expressed in terms of these 7 fundamental quantities. So every house you can build in science can be built from these 7 bricks. Okay. And in fact, everything we study in Physics 1, we will use only these 3 units. Okay. So length, mass, and time. Everything you study in Physics 1 can be expressed in terms of length, mass, and time. So for instance, here's energy, okay? The unit of energy is a joule. It is Newton meter, and it is meter square kg per second square. Okay. Here's a quantity you'll study, force. The units for force are newtons, the SI units. Okay. And a newton is a meter kilogram per second square. Okay. So everything in science can be expressed in terms of these 7 units, okay? The 3 we'll use as meters for length, seconds for time, and kilogram for mass. Smaller or larger units can be derived using prefixes. We'll come to that in a second. Okay? So here are some quantities that are measured in science, and you can see that everything, all those guys are measured using one of those 7 bricks. Okay. All right, so let's come to prefixes. Now, All right, so we are sort of hardwired to, how old are you?
26.
26. Yeah, how old are you in seconds?
That's math.
And that's, he won't tell me his age in seconds. Why doesn't he tell me his age in seconds? Because it'll be some big number, 1,645,342. I'm never going to remember that. Okay? We are hardwired to remember smaller numbers. All right, so if I want to convey the distance to Jacksonville to you, it's 156,342 meters. You're never going to remember that. Yeah. So, if you're measuring larger distances, a meter is not a good unit. Okay? So, to derive a more appropriate unit, we just use a prefix. Okay? So, meter is the basic unit for length. When you add this prefix, what is the prefix? The prefix in this case is 10 to the power of 3. Okay? So from the meter, you derive this unit. Okay? Now, in this unit, the distance to Jacksonville is 150 kilometers. And even I can remember that. Okay? All right, so that's the point of these prefixes. You can derive units that are more appropriate to what it is that you're doing. Okay, so for instance, a yottameter would be 10 to the 24. Okay, so if you wanted to measure the size of a galaxy, that would be the unit you would use. We don't use that, but I'm just saying. Okay. We use light years. So for instance, you guys know that you live in the Milky Way galaxy, and the Milky Way galaxy is about 100,000 light years across. Okay. So in astronomy, we use light years. Okay. But anyway, so if you're studying atoms, okay, atoms are about 10 nanometers. Okay. So an atom is a tenth of a nanometer. So 1 nanometer is 10 to the minus 9 meters. And okay, the size of an atom is about 0.1 nanometer. If you're studying cells, if you're a cell biologist, a cell is about a micrometer. Okay. So 1 micrometer, 10 to the minus 6 meters. Okay. So again, these prefixes are powers of 10. That'll give you appropriate units for whatever it is that you're doing. Okay. Okay, so every quantity that you study in Physics 1 can be expressed in terms of length, mass, and time. Okay? The SI unit for time is the second. And so we'll see how a second is defined. Okay. How's the second defined? Do you guys remember? Do you guys know?
It's defined by so many specific periods of cesium
Yeah.
within a
Okay.
nanosecond.
Yeah, so I want you to start 200 years ago. You're starting now. All right. So a few hundred years ago, this is how it was defined. This is the sun, this is the earth. This earth spins around its axis, and if you're there, when you're there, the sun is directly overhead. And when the earth completes one rotation, the sun will be back there again, okay, at zenith. And we call that 24 hours. Yeah. So actually this earth is the Earth is spinning and revolving, so it turns out that the Earth this is crazy. Why is it doing that? Okay, so actually when it comes to zenith, you're rotated through 361 degrees, but doesn't matter. So that's what we call 24 hours. And of course, if you're cooking something, 24 hours is a long period to cook, then we broke that up into 24 hours and so on. 1 hour into 60 minutes, and 60 minutes into 60 seconds. Okay? So that's how can we define the second. But we had to refine that unit of time. We had to make it more precise as our measurements got more accurate. Okay? And so like our friend said, here's how we define the second. Okay? So let me, okay. So here's a model of an atom. This is for a hydrogen atom. There's the nucleus, and the electron goes around the nucleus. Okay? This is what is, everybody know the model of an atom? Is there anybody who, you don't know the model of an atom? Okay. All right. You're familiar with the periodic table? All right, let's build an atom. Let's build lithium just to keep it simple. Where is lithium there? Anybody? Where is lithium? Huh? Period. Yeah, period 2, column 1, allied 3. That's lithium, okay? So what that means is the lithium has 3 protons. So here's the nucleus. Okay. And here are the allowed orbitals. Yeah. So every atom is neutral, of course. The inner shell has 2 electrons, and the lithium atom has 3 electrons. So there are the 3 electrons. Okay. 3 protons, 3 electrons, and the atom is neutral. Okay. The size of this atom is what we've been talking about. The size of most of these atoms are about 10 to the minus 10 meters. Okay. The size of the nucleus is 10 to the minus 15 meters. That's very interesting. Okay. Now, the most of the mass of the atom is right there. And this, so this drawing is not to scale. The nucleus is 100,000 times smaller than the atom. Okay, if this atom were as big as a football stadium, the nucleus would be the size of a marble. Okay. So an atom is mostly all empty space. Okay. Anyway, so there are all allowed, all kinds of allowed levels. Okay. An infinite number of allowed levels. Those are all empty. Okay. You can get an atom excited by getting exciting the electron from the ground level to a higher excited level. Okay. So if you shine light on this atom of appropriate frequency, it will kick this electron up there. Now that's an excited electron. That's an excited atom. Yeah. Now, of course, this atom doesn't like to stay there. Yeah. Within a billionth of a second, it'll get de-excited. What will happen is it'll emit light. And the electron will come back to the ground state. The atom will come back to its ground state. Of course, you could have excited the electron to this state, it would have fallen back there. You could have excited it to that state, it would have fallen back there, and so on. Okay. How many different excitations are there for a given atom?
6 for each of the different layers.
Okay, how many layers are there? An infinite number. Yeah. So there's an infinite number of excitations. They're all unique to every atom. That's their fingerprint. Yeah. You want to identify an atom, all you have to do is heat the heck out of it. Watch the light coming from it. Okay? That's how the forensic scientists, okay, detect those trace amounts of material. Okay. All right, so you know when the electron falls from here to there, it emits a unique photon. Okay? The energy of the photon is equal to the energy difference between these two levels. Okay. All right, now coming back to the reason we are talking about this is, okay, so like our friend said, so you're going to look at a specific transition for the cesium atom. You're going to look at a specific light coming from the cesium atom. Okay. So here's the photon coming from the cesium atom, and you put together a bunch of photons from cesium atom, then you have a beam of light. Okay, I'm speaking very loosely. Okay. All right, so now let's go look at another picture. All right, so here's an electromagnetic wave. It's called, so this wave is, this beam, if you want, is traveling in this direction. It is called an electromagnetic wave because it contains both an electric and a magnetic field. Okay, and if you were standing here, this electric field is oscillating like that. Okay, so let's do this wave. The beam is traveling in this direction. The electric field is oscillating like this. The magnetic field is oscillating like that. All right, so what we have is, we have a cesium atom. We're going to look at light that is a specific transition from the cesium atom. So here's this beam coming, and this electric field is oscillating like that. So you're going to stand here, and here's one oscillation. The electric field was pointing like that. That's one oscillation. Yeah. You guys understanding all of that? Okay, so you're going to count 9,192,631,770 oscillations from that radiation. That's when 1 second will pass. And that's the second. Why are we doing this?
So you can have them do it at a time.
To make sure it's precise and everyone follows the same rules, so you don't get
So,
GPS.
yeah, so you need this precision. We don't do it just like that. Everything is need-based. Okay? So nowadays experiments are done with such precision that you need this. Okay? So you can't make errors of 1 part in 10 billion. That's too large an error. Yeah. So again, whenever we go to all this trouble of defining all this, that's because we need it. Here's another thing about this. Okay. Okay, going back to this old definition of the second. What if you had a friend in another galaxy? He doesn't know about your orbit, and you can tell him all about your orbit, but this definition of the second is hard to convey to him. he understands this language. This language is universal. The cesium atom behaves the same way here as in the other galaxy, as in every galaxy. Okay. You can make this measurement here, and he can make that exact same measurement. He understands what your second is. Okay. All right, so this is the Planck time. We believe that's the smallest unit of time. Yeah. So this is an atomic clock, and it can keep time to an accuracy of a microsecond per year. Yep. A millionth of a second per year. So we've defined time. The three basic units are time, length, and mass. Okay, so back in the old days, here's how the meter was defined. A meter is roughly this big. Okay, a little more than a yard. Okay, so the meter was defined as the distance, 1/10,000,000th of the distance along a longitude passing through Paris, okay, from the North Pole to the equator. So 1/10,000,000th of the shortest distance, like that. Okay. Of course, nowadays that's not very precise. Things change, the Earth shifts and all that kind of stuff. We have tectonic plates moving all the time. So now that we have a precise definition for time, and the speed of light is constant everywhere in the universe. Okay. So we will define the meter as follows. It's the distance light travels in that time. Yeah. And that's the meter. And now here's a definition that, this definition won't change anytime. So you can leave notes like this, and people reading the notes 10,000 years from now will understand it. Your friend in neighboring galaxies will understand this. Okay? So here are universal definitions. Now here's an old definition of mass. The unit of mass is a kilogram, and here's a lump that we call a kilogram. Okay. And there are copies of these, and so that's a kilogram. Now there's another definition of a kilogram. There's so many silicon atoms is defined to be a kilogram. Yep. Also, a kilogram is defined in terms of the fundamental units, but we won't go there. I guess here are some of the fundamental units. That's the Planck's constant, h bar, c, and so on. Okay. So here are some of the fundamental constants, and it's defined in terms of those. Okay, we want to understand this expression, order of magnitude. Oftentimes, we'll be interested in just rough answers. Okay? So, for instance, let's say you ask me, how many students are there? Let's say somebody asks you, how many students are there at Daytona State? Okay, I don't want a precise number, 15,342. I just want rough numbers, 15,000, 20,000, okay, and so on. So here's what order of magnitude means. Okay. So let's say you have a number 756. Okay, this is close to 1,000. Okay? And 1,000 is 10 to the power 3. So the order of magnitude of this number is the power of 10 it's closest to. Okay? That's what the order of magnitude means. How about this? What's the order of magnitude of this number?
2.
2. Okay, this is close to 100. Okay, that's the order of magnitude. Okay. So there's a more precise way to calculate it if you want. Yeah. So let's say sometimes this can be confusing. But we won't worry about this precise way. I'm just going to show it to you. Don't worry about it. I want you to just remember the quick way. Yeah. So here's how you precisely calculate the order of magnitude, 495. What is the order of magnitude of this guy? So if you did it the quick way, you would round this to 100. Well, this is less than 500, so you would round this to 100. I mean, you would guess this to be 2. But here's how you would calculate the order of magnitude. You take log to base 10. You're figuring out this number. Okay? Would be x, and log to base 470. .67, and that would be 3. Okay. Anyway, we won't be doing that too often, and don't worry about that. So the order of magnitude of a number is roughly the power of 10 it's closest to. Okay. Again, so this illustrates, so when you're studying galaxies, the order of magnitudes you live in is 20. Okay. If you're studying cells, if you're a microbiologist, the order of magnitude you're living in is -5. Different orders of magnitudes are different lives. It's different expertise. If you're a nuclear physicist, your life is spent in order of magnitude of -15, and so on. Okay. So here are some. So here's the range of stuff we have studied. The mass of an electron is 10 to the minus 30 kgs, and so the mass of a galaxy is roughly 10 to the 42 kgs. Of the universe is about 10 to the 51 kgs, and so on. So I'll point out an interesting thing in this picture. Right. So the mass of a proton is roughly 10 to the minus 27 kgs. Okay. So here is the mass of normal matter of the universe, 10 to the 52 kgs divided by 10 to the minus 27 kg. Okay, what does this give you? That's the mass of the universe, the normal mass, divided by the proton mass. So that gives you the number of protons in the universe. Okay? Protons and neutrons. So that's 10 to the power 79, roughly 10 to the 80 protons. Okay. So that's kind of neat. Okay, so in these little diagrams you can figure out all kinds of stuff. So here's some times we measured the age of the universe. It's about 13.8 billion years. The age of the Earth, how old is the Earth?
5 billion.
Yep, 4.5 billion years. Look at that. Duration of a nuclear collision, 10 to the minus 22 seconds, and so on. Okay. You will be doing this a bit, okay? So you will need to convert units. Okay, so here is a speed, 75 miles per hour. That's converted to meters per second. Okay. And the trick is as follows. Okay, you guys all know what is 5 times 1? 5. So you can always multiply something by unity. Okay. So 1 mile is 1600 meters. Okay. What is 1 mile over 1600 meters? What is this equal to? I'm sorry? 1. Okay. What is 1600 meters divided by 1 mile? 1. Okay. Now you can multiply anything by 1. Okay. So when you're converting units, all you're doing is multiplying by appropriate factors of unity. So here's 75 miles an hour, and this is unity. And why did we multiply that? The mile will cancel. Yeah, meters. Yeah. And similarly, you want to cancel the hour. So 1 hour over 3,600 seconds. That's also unity. So all you did was multiply this number by this unity and that unity. Okay. Okay, so that's how conversion happens, and that's equal to 33.3 meters per second. Yep. Which one is faster? They're the same speed. Yeah. This is the speed expressed in Spanish. This is speed expressed in English. Yeah. So different units are just different languages in which you're expressing stuff. Yeah. Here's a good technique to remember. I mean, good fact to remember: dimensional analysis. And what this is saying is the following. When in a lot of physics, laws are expressed as mathematical equations. Okay. When you have an equation, if you have apples on the left-hand side, you can't have oranges on the right-hand side. You have apples on the left-hand side, you have to have apples on the right-hand side. Okay. So you can't have this. And that's all dimensional analysis does. Okay. So here's an equation, for instance. Okay. Actually, let me do this. So S equal to VT square plus 0.58T. Okay. So let's say somebody gave you this equation. Without knowing any physics, you can decide based on this if this equation has the chance of being right. Okay. All you're going to do is you're going to see if you have apples on the left-hand side. You're going to make sure that you have apples on the right-hand side. Okay. And of course, you have to know something about the symbols. S represents distance. Okay. What are the units of measurement of distance? Meters. So there's the apples on the left-hand side. Okay. So what you have to make sure that this term is an apple, this term is an apple. Okay. V stands for velocity. Velocity has units of meters per second. T stands for time, and that's time square, so second square. So this first term is meters times second. That's not an apple. So there's no way this equation is right. Okay, and that's all dimensional analysis is. Okay. So it's a quick way to test and see if an equation has the possibility of being right. Okay. So by using this technique, you can eliminate a whole bunch of wrong equations. Yep.
I'm sorry, what does the lowercase a stand for?
I'm sorry?
What does the lowercase a stand for?
Acceleration. So that would be meters per second square and then times second. So that one doesn't have the right units either. Okay. Now this equation is correct dimensionally. S equal to Vt plus 0.5 AT square. S equal to Vt, 3Vt plus 5 plus 7 AT square. Okay, now here's the ding against it. this is dimensionally correct, this is also dimensionally correct. But this is the correct equation, okay? So dimensional analysis can tell you the right equation up to constant factors. Okay? You have to figure out the constant factor correctly by taking an actual physics course. Okay? Okay, here's Mr. Fermi. He's a famous physicist. And he was famous for doing quick calculations in his head. Yeah. And so you are doing rough calculations, and this is a good technique to learn. So let's say you wanted to do some kind of large calculation. And to do a precise calculation would cost too much, but you do a rough calculation and you know the ballpark answer. Okay? So let's figure out something. Okay, I don't know. Let's say how many burgers are sold in a day, in a year in Florida. Or how many liters of water are drunk in the US a year. What do you want to calculate? Or how many pounds of food are eaten by people in the world in a year? Okay, how about we do that? Okay. We'll calculate how many kilograms of food are eaten by people in a year in the world. Okay? So you have to know some stuff, but are we interested in an accurate calculation? No. We just want a ballpark number. Okay? So you have to know some things about the world. How many people are there in the world? 8 billion. Okay? So we want round numbers. We'll say 10 billion. 10 to the 10 people. Okay? How much food do you eat in a day? About a kg, 2 pounds? We'll say roughly. Okay? 1 kg. Per day. How many days in a year? 360. We'll say 400 days. Okay? There you go. 4 times 4 trillion kg of food are eaten per year. Okay? That's a Fermi calculation. Okay? So that's the idea, and okay. So that's a useful technique to learn in various situations. Okay. Which would you rather have between these two guys? Hmm? The top one. Okay. Here you're more, okay, so what this is representing is, okay, this is more of an accurate measurement, but the precision is less. This is more precise, but it's not accurate. Okay, so here somebody's, okay, so measurements can be accurate but not precise. This is more accurate but not precise. Or they can be precise but not accurate. Okay? So here's somebody who has a very precise scale or a very fine scale in measuring this length, except that they're starting from here. Okay? It's like giving somebody a Ferrari and they're driving at 30 miles an hour, The precision of a measurement is conveyed by the number of significant figures. Okay, so if you can accurately measure something to 10th of a millimeter, so 5, 3, 4, 6, 7. Yeah, so the number of significant figures tells you how precisely you're making a measurement. Whether you're doing an accurate job, that's a different story. Okay? the rule of the significant figure is the last digit written down in a measurement is the first digit of some uncertainty. Okay, so when you report a figure to that, that's the digit on which you have uncertainty. Yeah. Okay, so this has 5 sig figures. Now I'll show you one more thing. Yeah. We'll do one more example and then we'll stop here. So how many significant figures does this have?
2.
Hmm?
2.
Okay,
Depending on, there's no decimal point.
okay, so to decide how many significant figures it has, you have to write in scientific notation. Okay, so this is 1.5 into 10 to the power of 3. This is 2 sig figures. Okay. Okay. So to convey the number of significant figures, you have to write in scientific notation. What is the difference between these guys?
Decimal point.
Okay, what this means is you have $1,500, give or take $100. This is saying you have $1,500, give or take $10. Okay, that's the digit in which you have uncertainty. You have $1,500, give or take $1. Do you guys understand the difference? Okay. So that's what that's about. Okay. All right, guys, so that covers the first chapter.